Hi, I'd like to talk about the problem Listen to Your Boss that was at ACPC 20, the Alberta Programming Contest. In this particular problem, you were given a tree of employees and you were asked a simple question, which is whether two employees, given a pair of employees, whether they were part of a supervisor chain. In other words, whether one employee was a supervisor of another employee. And to translate this into tree language, it was asking you, given two nodes, whether one node is an ancestor of the other node. This is a good application of the so-called parenthesis theorem that allows us to determine this for a tree. To show you how this works, we'll draw a tree here. So this is just one tree that I'm just a binary tree, maybe, or maybe let the tree go down like this. We perform a DFS traversal, and we will be assigning a timestamp to each node. And the timestamp just increments. We assign a timestamp when we enter the node and when we leave it. So we would start out with the root node. Here we would assign timestamp 0. We go to this child, timestamp 1. Then this one here, we would enter the timestamp 2. Now we would leave it. Now to leave it, that means timestamp 3. Then the next step would be to enter this one. So this would be 4. And we would leave that at 5. At this point we return, we would leave this one at 6. We would enter this node at 7. We would enter this node at 8. We would enter this node at 9. We would leave it at 10. Enter this at 11. Leave it at 12. Leave this one at 13. Then we would enter this one at 14. Leave it at 15. Leave this one at 16. And then arrive here at 17. So each node has two of those timestamp labels associated with it. Now, in this case, what the parentheses theorem says, if we have two nodes, okay, so for example, if we have this node here and this node here, we can make the decision whether this node is a descendant of this one simply by comparing those red and blue numbers. Specifically, that is the case since 7 is less than 9, and since 10 here is less than 16. And so, this has to be true that if you have any node and there's a subtree in here and we have an ancestor in here, then it's clear that this ancestor has to have been entered later. So the red number has to be greater, and also that this node has to be left later as well on the other one, so that the second inequality holds. If we compare to two nodes where this is not the case, so for example, this one here and this one here, we would find that that here in this case 1 is less than 8. Okay? And in the other case, we would find that 13, however, is not less than 6. Okay, so this would not be in an ancestor relationship. That's the idea, and this is called the parentheses theorem, right? We can just think like this because it gives a range for those numbers. Let's see how we can implement this algorithm. I started out with a fast scanner, and so now let's read the input. The first input here is the number of nodes in that tree. Okay, we'll call that n. So n tree nodes. The root is at 1 in this particular problem. The next number is the number of queries. Because what makes this problem challenging is that this question of are these two nodes ancestors of each other needs to be answered many times. Because if the answer just once is very simple, you could traverse this tree, and this DFS preprocessing only makes sense if you want to do it multiple times. Okay. So then we read the tree itself, and this is going to be n-1 entries that follow. The tree itself, we're going to represent it as an array of, I'm going to call it children, and this is going to be a new list with, in this case, n, since we have n nodes. Okay? And all of these need to be, as it's usual in Java, they need to be initialized. We do that here. Children of I is equal to a new array list. Okay, so now this is being read in, and each entry is like one entry, and this gives the parent. Okay, this is a very common way to notate trees by saying, this is the parent. This is all zero based, so parent. So we say the parent of node number I is P. Okay, except here I is counted from 0 to 1, but the first one is actually node number 2, just number 1. So we will do I plus 1. So we're going to be saying that so the parent of node I is P. That means is that the children of P that we are adding node I plus 1 in this case. Right? And then so then what follows then, we need to read those queries. So from 0 to q I plus plus, and the query has two a and b, and they both need to be input, and we are correcting them to be zero based by subtracting 1. And here we're going to basically have to say, if is whether is ancestor the direction AB. In this case, we are outputting yes or no. The output in this problem is actually the other way around. If it's not an ancestor, you should output no. We can tweak that. Later. So here we need to do a DFS, and we need to start a DFS at the root node, which is root is 0. Okay. So let's program this DFS. It's a tree, so it's pretty simple to do. We can do this DFS by going to the children in children of node U, and in order to do that, we need to be able to make this a static variable so that we have access to it. But we still need to initialize it when we know the number of children, which is here. And we also need to keep track of two arrays for those times, right? So we're going to call these times, we're going to call them in, and I'm going to call them out. Okay, so in and out also these, so in needs to be an array of ins, and out needs to be an array here as well. As we do the DFS, so we iterate over the children and we perform a DFS for each of those children, but we also record our in time. So the in time of U is going to be recorded to be the current time, which is then incremented, and the same goes for the out time. The current timestamp, we keep that here as time, and so this is all we need here. And then we need to implement our function, whether I guess we have let's say a parent, and we have a child, and so when is an ancestor, that's true if the red time, which is the in time of the parent, is less than the in time of the child, and the out time of the child is less than the out time of the what we think is the parent. Right? So let's see if that works as advertised. I'm going to call it T. I'm going to T and time in, time out. That's what I usually do. Time in, time out, and that change. And so let's see what it says for the sampler input. In this case, it would say no, because I made a mistake. So let's check what is going on here. Okay, so the first thing is let's output the tree that we actually built to make sure that the code that reads that tree is correct. Okay, so this tree is the first one is the root. So this is 0. It has two children. One child is 1, the other one is 3, and one has a child that is the node number 2. That is actually the correct tree that is given in the sample input in this case. Okay, so then the second thing to double check is what do those arrays look like? This is in and this is out after the tree traversal. So in this case, the times would be 0, 1. Then this one should be 2. Its out time is 3. Out time is 4. And then here we have 5, 6, and 7. It looks correct as well. Okay. So yes, the problem is that it is asking the other direction. Okay, so BA asking is this an ancestor of the other one? And so if we do this, then we run this, then we get the answer, except we get it the other way around. The question was if it's an ancestor, if it's basically in the chain of command, then they can't ignore it, and otherwise they can ignore it. Okay, so let's remove those debugging statements and test it, and it gives the right answer here. Let's verify that, and so let's see if we can submit this. And that's accepted. Okay. So this is called the Parenthesis Theorem, and it is a neat little application of DFS, very simple DFS, computing an in timestamp and out timestamp, and allows you to answer the question whether one node is an ancestor of another within a tree.